Now we have talked about the boosting, the basic intuition behind boosting, what actually the boosting are. So now I will start talking about a gradient boosting. Okay, so gradient boosting is one of the most powerful algorithm that I've seen so far. One of the most powerful algorithm which is yet to just learn. It's very to have a good in your toolkit. Okay, so I'm on a Wikipedia page which I found a great algorithm, which is again which just tells you a very good intuition behind gradient boosting, rather than just I make use of my blackboard. Either way, I will make use of my blackboard over here. Okay, so what is gradient boosting? This is a great question. So gradient boosting is a boosting algorithm that just converts the weak learners into the strong learners. Okay, so let's start with this gradient boosting, and you can search for gradient boosting wiki, and then you will see the gradient boosting Wikipedia articles, and then you can read the full articles. Either I will cover everything in short period of a time, but I've already covered some of them, and of my I have covered more than this Wikipedia. Okay, so I will give you some real world examples of gradient boosting also, where it is used and everything. Okay, but first of all, let's understand this algorithm. Okay, so let me see my pen is at least working or not. I hope that this is working. Yeah, this is working great. I'm just happy that my ink is working. Just if the ink to go, if you're watching, please help me to improve this. It is not that much good. Okay, just to improve this, but it's very good tool. Sometimes it lacks, but it's very good tool. You check it out, it's very good, great, for free. Okay, so you have this training data, which is a input training data. You have this input training data, which is the set of, let me write the training data, which is simply your xi and yi, and simply goes from I equals to 1 all the way down to the n. Okay, or m, which is our, let's stick to our formal notation, which is m, which is the number of training examples, number of training, or the size of our training examples. Okay, so that's our given data, and we have a differentiable cost function. Then we have a differentiable cost function. Okay, so what do I mean by differentiable cost function? Differentiable cost function means that this cost, because we take out the derivative of our cost function, we take out our derivative of our cost function with respect to some value. Okay, so let's take we are taking out the derivative of our j of theta, partial derivative over j of theta. Okay, so that's the basic that's the differential equation that I know. If you're a calculus student, then you might interpret that we have a differential. But if you're not able to get what is this differentiable, feel free to leave this differentiable. Just think that it should be derivable. Okay, for our gradient descent, or we will because we have to take out the derivative of this particular loss function with respect to some weights. Okay, so we are given a training set, which is dtrain. We have a given a training set which is value xi and yi, which goes from I equals to 1 all the way down to the m. Okay, where is my eraser? I think that this is my eraser. Yeah, I equals to 1 all the way down to the m, and then we have a differentiable equation is given. So let's stick to the j of y f of x, and this is simply just the error, means just a minus your more appropriate value for each and particular examples. I equals to 1 all the way down to the m, and then we square it all up. Okay, so that's our cost function. Maybe it can be mean square error, or it can be log loss for classification, etc. Okay, then we are given the iterations. Then we are giving the number of iteration, which is m, and m here is the model. M here is the base learners. M here is the number of base learners. Okay, so this is the number of base learners, which is m. Now let's start with the algorithm. So what this algorithm tells you, so let me choose the different colors so it might make sense. So we initialize our model with some constant value lambda, in that case we have in alpha, but now we had changed a little bit that we have our favorite lambda. Okay, so we have to find lambda. Okay, let's just think of it as that we have a lambda, that we have to find that lambda that minimizes this training error, this loss function. It should be told here, but I told you here just in my excitement. So what you do, you initialize your model with some lambda that minimizes this cost function. Okay, so this first to initialize this, and we will see how this lambda is computed here. But first of all, you initialize it, and then what you do, you iterate through each and every model. Okay, first you do this for first model, then you do again for second model. Means you apply a for loop where for m equals to 1, first you 2m, means you want to go 1, 2, 3 all the way down to the m. Okay, so you do this, and then okay, so here then what you will do, then I hope that then you initialize your model, then you compute the residuals, you compute the pseudo residuals, and then here it is named as r subscript I and m here denotes the number which model, and I here for each training examples. Okay, so here you compute the I and m, and then you take out the partial derivative. Oops, why it is not working? Partial derivative. Hey God, please help me. The partial derivative of your cos function yi, and f of x. So this is your loss function with respect to this function. Okay, f of x, your model predicted value. Okay, and then you want to fit your model onto your previous residuals. So for you go to I equals to 1 all the way down to the n. So here you take out for f of x, means means here you are fitting your model, means just you are making the model to be f of m minus 1, means the previous model. Okay, so you compute those residuals, and then you fit the base learners. Okay, that I've just showed you in my previous just in a boosting, that we fit the residuals. So let's take example, we have m1, m2 and m3. We have taken the residuals, and give some residuals. This m1 is trained to fit the residuals from m1, this m2 trained to fit the residuals from m2. Okay, and this is m3. Okay, so it is trained to fit the residuals of m2. Okay, so then you fit a base learner or a weak learner. Let's take an example 3, closed under scaling of h of mx. Here is your two residuals, two pseudo residuals, means you fit the learner to fit the residuals from the residuals got from the previous base learners. That is to train it using the training set, this one. Okay, and now here RIM is in our case, which is LI on M model. Okay, so then you fit your model that I've already showed you, just similar that we have seen, and then you compute the multiplier, which is a constant multiplier lambda m. For each model you have lambda m, okay, which is a one-dimensional optimization problem. For solving the one-dimensional optimization problem, so you may ask, yeah, Yush, why do we are choosing this lambda m? So for solving one-dimensional optimization problem, going into 1D optimization is out of the bound of the course, but you can see on the link. Okay, how you compute lambda for each model that minimizes the loss of y, which is the ground truth, from the previous model, plus lambda times our just model that we have now. Okay, now what you do, you update the model. Now you update the model to be the model to be fitted by the model that fitted the previous residuals. Okay, so f of mx, here m is our model number, the means model number, then we have this f of m minus 1 previous model plus lambda m, which is some constant for solving the one-dimensional optimization. Okay, because we are taking the partial derivative of our loss function yi and f of xi with respect to f of xi, and f of xi is our model predicted value. Okay, times h of mx, and then you get your output as a f big model m big model all the way down to the x. Okay, so here you when you cover all of this, when the loop is done, then you get the final model, which is f mx, that is simply f of m minus 1x plus the previous model. This is previous model plus the model that we got after solving this 1D optimization problem. Okay, so that's the gradient boosting algorithm that I really hope that you understood. But let's just as a recapitulation to help you understand it a little bit much better to understand this problem. Okay, so what we do, let's understand what we do over here. So we simply, first we have a given our training data. We have a training data xi and yi going from I equals to 1 all the way down to the n, and n here n here, I just hope that it should work now, and n here is your number of a training, your number size of your training set. Then you have a differentiable loss function with the number of base learners that you want. Okay, then you initialize the model with some constant. Okay, then you apply a for loop. In that for loop, you take out the residuals. For and then you name it as a r subscript I, which is the number of training the index of the training example, and m is your number in the index of your model. Okay, minus the taking of the derivative or partial derivative of your loss. Okay, okay, and then you fit a base learner or a weak learner, because it just makes you a weak learner to the strong learner. Okay, to closing under h of mx, which is your got from the weak model, means you just fit the base learner to the residuals. So it's simply that you are going to fit your model into xi and your li, which is simply li is this. Okay, now you compute the multiplier lambda subscript n for each particular m, means the model index, for solving the one-dimensional problem. So it's just you find the lambda m that minimizes the loss that you get yi comma the output from this model. Okay, this is the whole model. Now this is a previous model, this is a new model that is fitted to fit this residual. Okay, and then you update your model. Okay, then you have to output a big model, which is f of mx, that is simply this f m minus 1 of xi plus your big model. Now you just after your full iteration, you'll be ending up being a big model. Okay, so that's the basic intuition behind gradient boosting. I really think that you understood about gradient boosting. Now it's time for getting into the something called as a regularization and shrinkage. Okay, but before that, why do we need even regularization and shrinkage? So why do we need, as we have already talked about, that we have in boosting, we have high bias, let me see the recordings are on. Yeah, oops, we have our high bias and low variance problem, sorry, high bias. So we use boosting to reduce the bias, So high bias is just doing that on a training set. So we just after each iteration we are fitting the previous model residual. So yeah, it is making a null. It means it is doing very good on training set. So very good on training set. So it may happen that it may start overfitting and our low variance goes to high, where going to high variance, means our low variances start increasing and now it's converts to high variance. So that actually can cause overfitting. Okay, so for avoiding, we add regularization and shrinkage, which is again shown in the Wikipedia page. Let's see. So here I think that I can teach you better than Wikipedia page. Okay, so you have this big model, f of m x, which is here you have a h0 x plus you do for I equals to 1 all the way down to the h, is number of your model, lambda m, or you can say m, the number of a model, okay, h of mx. Okay, so that's your model that we, and then what do you do then? If the number of a base models increase, means it will fit more residuals. If it will fit more residuals, then your overfit will then it will start overfitting, and if it is start overfitting, then your variance will start going up. Okay, so that will cause the problem. So what you do, you shrink by a factor of there's a Greek letter that I even don't know, that is something called as a v. So let's assume that is a v, which is a parameter v. Okay, so we have our parameter v, which will help us, which is just a parameter for controlling it just shrinks to do not go that much, means it gives a weight. It is just a learnable parameter, just gives weight. And empirically it is found that v equals to 0.1 tends to be a dramatic improvements in your models. Okay, so that's why we use this v to be 0.1, and again your v should be in between, 0 and 1, and it's found that v equals to 0.1 would be dramatic improvements in your models. Okay, so you add a new weightage to that model, means to this model. Okay, you add weightage to this model that I've just shown to you, add weightage to that model, and that's called the learning rate, for how much rate it should learn. Okay, so that's we add v to that model. So let me add that. So what you do is you just shrink your model big model by going f of m minus 1 x plus v times lambda m h of m x, and v here is in between 1. Okay, and empirical is found that b equals 0.1 works best. Okay, so that's about gradient boosting, and I really hope that you understood this also. Okay, so now it's time for we will take a look at implementation. Okay, so now we will take a look at the implementation of gradient boosting classifier and gradient boosting regularization. Okay, but before that, let's see the training time complexity of your model. So let's recall of decision trees. And decision trees, we have our train and runtime complexity. So here we in decision tree dt, I'm writing dt, we have all n, why I'm writing this, n log d, and here d, and then random forest you have o order of n log n, number of a decision tree means k. Okay, now when gradient boosting decision tree means here we just take our base learners as a decision tree rather than different models. So we have o n log d times the number of models. Okay, so that's the basic time complexity of your gradient boosting decision trees. Okay, great. Now we will see something called as the implementation of this gradient boosting decision trees in scikit-learn API. Okay, so let's see. So let me open gradient boosting implementation. Okay, in sklearn. Let's see. Yeah, here we found. Just wait for a few seconds, it's just loading. Okay, great. So now here you are on a page of scikit-learn API gradient boosting classifier, and then you can see over here that now let's see some of the parameters that we are over here. So here that you have a loss, which is deviance, deviance refers to the log loss, and exponential refers to the which is just the adaptive version, which is if you set exponential, then your gradient boosting will be called as a adaptive boosting or ADA boost. Okay, so in adaptive boosting, it is more pronely, we will see the implementation. So in ADA boost, it is more pronely focusing on unclassified. Okay, more pronely focusing on unclassified, but it's not being used too much. Okay, so we have a loss equals to deviance, which is used as regularization loss or log loss. Okay, then you have a learning rate, means the rate to shrink the contribution of each tree by learning rate. Okay, so this is used to reduce your variance. Okay, so that's your model does not start overfitting. Okay, so this is your learning rate, which is default 0.1 and leave it 0.1. okay, because it's found that most dramatically that they work best in most of the cases. And then you have a number of estimators, which is number of decision trees, subsample, criterion, min sample split, min sample leaf, min weight fraction, max depth for each tree, min impurity. These are particularly for each trees. And then you have let's see something more of that we have a validation, eternal change, and then total CCP alpha. That's not too cool. Okay, so we have this, and these are some of the hyperparameters that I know that you had understood everything. Okay, so you can see more about this in the parameters in detail here, but we have already talked about decision trees already. Okay, so let's see the implementation. Means the implementation of this gradient boosting is just one line of code, which is here. And you can use predict probability. It simply gives the probability of that being true. Okay, for that class. Okay, so first you import from sklearn.ensemble, import gradient boosting classifier. Here is your data, means, and then you call your with n estimators, learning rate 1.1. okay, 1.0 max depth, random state, and then you fit it, and then you get your score. Okay, so that's the basic intuition behind a gradient boosting classifier. Okay, now let's see the gradient boosting regressor. Gradient boosting regressor, regression in sklearn. Okay, so this is a very good to learn from the documentation. Okay, this is very good to learn from the documentation. So let's see. Okay, here we are on documentation of a scikit-learn API. Now what we will do, we will just let's use the pen, and then you can see over here that we have a loss function to be optimized, means L as the refers to the least squares, LAD means least absolute deviation, is more robust. Okay, so we have a Huber, then you have a quantile, but the default is LS. Okay, then you have a learning rate, how many, this is for shrinkage, then you have a number of estimators, then you have subsample, criterion, min sample split for each particular decision trees. These are for each particular decision trees, and then the same thing that we have seen so far. Okay, so now we are this is the basic for decision trees, and I hope that you understood. Okay, now let's see the implementation of this. I'm a little bit going fast because I have to teach also that XGBoost and ADA boost. Okay, so you just call the gradient boosted regressor, then you call your train test split, then you split your data, and then you call your gradient boosting regressor with the default parameters. Okay, then you fit it. Okay, and then you simply do the gradient boosting regressor, then you score it, and it uses the sum scoring parameter, means the log loss, or sorry, not log loss, it maybe it uses R2 or MSE, even C. Okay, so that's the basic intuition behind how we implement regressor and classifier, which we will do in project just to showcase you how you can assess from documentation. It's very good to learn from the documentation. Now it's time for learning from that we'll learn about XGBoost. We will learn about but before that let's learn about ADA boost. Okay, ADA boost. So let's see, I want implement sklearn. Okay, so if you set your loss to be exponential, okay, to be exponential, then it will be equivalent to ADA boost classifier. Okay, so it will set your loss to be like this, and it's just the same as that we have already talked about. We have two algorithms given by Sammy and Sammer, which is in Sammer, which is also for logistic regression, if you have seen, it's the scikit-learn API. Okay, so how you implement from XGBoost classifier, then you call this and then you fill your model and then you are done. Okay, it's very simple. I think that but just remembering the concepts is very important, because it's not always you have to implement maybe your own something algorithm in your company. Okay, you may think, yeah, you can't we just study the implementation? No, you cannot study. Okay, but scikit-learn API is very slow, very slow, but it's great. But what you can do, you have to in some companies for production, because it's a Kaggle winning algorithm, that we need to understand what is happening, how we can tune the hyperparameter. Okay, so here you can see again for regressor. Okay, and here you have a loss equals to linear, and then you have a square, and then you have exponential. Okay, and here maybe we do have a not loss. You can see state the number of a classes, how many number of a class with a classifier. Okay, so now we know about this, and I really hope that you understood the following. Now it's time for learning about extreme boosting, one of my favorite, but I think XGBoost is not used in production. Not uses too much in production. Maybe I'm not right over here, but I think so. Okay, so now we will learn about XGBoost, which is one of the most popular algorithm which I've seen so far. Okay, okay, it's a good algorithm. It's a good algorithm, but it's one of the best algorithm that wins your Kaggle competition. Okay, so now we will see what XGBoost does. It's just the advanced version of gradient boosting. It does have gradient boosting decision trees, plus it has randomization with row sampling plus column sampling. And so in gradient boosting we are not doing this, but it's at randomization, which is row sampling plus column sampling. So that's why we name it as a extreme gradient boosting, and it works best. Okay, it works brilliantly in some cases in machine learning problems. Okay, but it needs fine tuning a lot. Okay, so you have a gradient boosting decision tree. Now you have a row. It's just how it differs from gradient boosting decision trees. You do the randomization by doing feature bagging, and then you have a row sampling. Okay, and it's just for a simplicity. Let me explain you what we tend to learn about this. What we do, we simply sample the rows as well as the columns for our data. Okay, and specifically for bagging we don't do columns, we don't do column sampling, but in a random forest we do both. So in XGBoost we do the gradient boosting decision trees as well as a random forest plus column sampling. Okay, so that's what we do, randomization, and that's the XGBoost. Okay, so now we will see in detail what actually the XGBoost implementation, XGBoost, from the official documentation. But it is of course implemented in the implemented in scikit-learn API. But it's very good to use because this is fast actually. It is fast actually. It's very good to learn from here rather than there. Okay, so I think that we can get the Python package, because we have different package now. Setting parameters. Oops, where it is XGBoost Python package. Okay, so here we have some parameters in XGBoost. I think that my Brave is not working. I have to again switch to my favorite Chrome. Why I have switched to this? It's bad. Brave is actually not good for me. And in some cases, actually, who am I to say bad? But it's good. But it's all, of course, sometimes it does very bad. Okay, so let's see some of the parameters. So we have different packages that already been implemented this algorithm. So here you have booster, which is GB tree, means gradient boosting tree. You can use GB linear or Dart. Means we usually use GB tree. Then you have validate parameters. Default to false means it's just you want to validate your parameters or not. then default to maximum number of threads, then you have an evaluation matrix, then E term is learning rate, okay, is 0.3, okay, gamma, which we have seen, which is the constant, which is 0 as default, and is just we just randomly initialize means, and then we find a good like gamma. And then what is the max depth for each tree, and you can read the documentation over here more. Minimum child weight, minimum delta step means what is the step should one maximum delta step we allow each leaf output to be. It means there is no constraint, okay. If means it's just like that, it's just helping you to not too much proning to overfitting, means more robust model. Okay, so you can see your lambda means L2 regularization like lasso, and this is for regularization, that is alpha regularization. Okay, then we have a tree method, which is XGBoost construction algorithm using XGBoost. You can see the reference, you can see obviously see the reference. It also supports hist and etc. Then it's have a scale post weight updater, which is process type, grow policy, maximum number of leaves but is default to 0 to be added. Okay, so max bin predictor, then we have a GPU, CPU, but this needs a lot of fine tuning. It takes a lot of time in CPU. Okay, so we have this much, and you can see more about this. It's a very long set of parameters, but we usually use the main parameters that we have listed. Okay, so you can see a Python package. First one, you want to install it. You can just pip install XGBoost, and then you just call xgb.d matrix. First you convert that into a d matrix, then you do that. Means you can do also for pandas using the scikit-learn API, but it's okay to use it. But you can see over here implementation sklearn. It's also for a regressor that we have seen. I think that they have removed. I think not, they haven't removed. No worries. So you can see from here how it is used and how we train this model and how we save this model. It's just like a neural net. As you know that TensorFlow has also added decision trees and like that in ensemble learning. It started adding because one of the most powerful algorithm in ensemble learning. Okay, so we have seen a lot in decision trees. Okay, in ensemble learning, like bagging and boosting. Okay, so now one last step is left, is stacking of your stacking. Okay, so after this section we will start with the stacking to help you to better understand what actually stacking is, and it will obviously help you. Okay, so we have seen a lot of applications of this, and I really hope that you enjoyed it also. Okay, so this section is just amazing. We have learned about boosting, we have learned about gradient boosting, then you have adaptive boosting, then you have learned about XGBoost. Okay, and so one of the projects will fine tune, will use XGBoost, AdaptBoost with fine tuning. Okay, one of our project. Okay, so that's it for this section. In the next section we'll start with stacking. It's a 20-minute session on stacking will take, and then we just with some summary or revision of ensemble learning. Okay, so let's meet at the next section.